In these sections, we look at introduce definition of the stress component in 3 dimensions. Here, in general, an elastic deformable object under any kind of the loading in XYZ Cartesian coordinate systems. So here, follow our procedures. We simply interested in a point inside this material model. So we simply, for example, we take the free body diagram, and in such a particular free body diagram, we cut it in a way to expose a section. That section has the normal in the x direction. And if you like, you can pick any internal cut, cross-sectional cut that has the normal to y or z direction, up to you. In these particular selections, this is the point we're interested, and this is a plane has the normal to x direction. So we define this as called the x plane, and it is simply because its normal direction is in x direction. We give a name called the x plane, and in the x plane, under the symbols, we could have the directions in 3 directions in x direction, and this is by chance normal to the x plane, so we're using F. And in y and z direction, the 2 directions are parallel to the x plane, so we use V. Okay, and actually using delta, and meaning that is the corresponding small amount just happened on this small area, and which has the area delta A. So here is a magnitude, here is area. Divide magnitude by area give us stress, and this is derived from the normal force, so that's a normal stress. In a similar way, divide magnitude, which is a shear force, by corresponding area, shear stress, and shear stress. So from here you can see this notation. Basically here, the x-plane, that meaning the directions of this plane is that go to this symbol here, go to this symbol here, go to this symbol here. And then as far as the directions of the stress, and for example, this stress induced shear stress is in y direction, so that one, let me use this one. So this one pointing in y direction, this is induced, so using y again. This stress pointing, that is from this component, and that pointing to z direction, so pointing to z direction, so that go to here. Okay, so basically the symbols tell us is this. The first symbol give us is which plane the stress is. The second symbol is about which directions the stress pointing to. So keep this symbol in mind. We can have more exercise here. So we can exercise. So from here we can start with saying this is our x-plane. Okay, and per our coordinate system, it has a normal to x direction, so we call it x-plane. So here, per our symbol, and this is the normal stress, we're using sigma, x-plane, pointing to x direction. Okay, so this is the shear stress because that's parallel to the plane. So shear stress, we're using tau. Okay, this shear stress is in x-plane, pointing to y direction. This is the shear stress, and in x-plane pointing to z directions. Okay, so we can have more exercise. So this is the y-plane. In the y-plane, this is the normal stress in y-plane pointing to y directions. So this is the shear stress in y-plane pointing to x directions. So this is the shear stress in y-plane pointing to z directions. Okay, so this is the z-plane. So this is the normal stress in z-plane pointing to z directions. this is the shear stress in z plane in x direction. This is the shear stress in z plane in y direction. So maybe in here, in the previous page, is the beta notation make everything consistent. This should be sigma xx. Okay, so that is for the stress component. And one additional comment is this. Here, if we only look at the distribution of the stress around the z-plane, so this is z-plane because this has the normal to the out of the paper z direction. So this is the z-plane. Around the z-plane, we have the normal stress component in x directions, and we have the normal stress in y directions. And here for this slide, actually I want to more focus is on the shear stress. We have a shear stress in x plane in y direction, in y plane in x directions. Okay, so what I'm saying, so this plane, okay, this plane normal to the x direction, so this is called the x plane. And this plane has a normal in y direction, so that's what I call the y plane. So the shear stress on the y plane pointing to x directions, y plane pointing to x direction, tau yx. The shear stress, this one in x plane pointing to y direction, so that is this one. Okay. So now in this slide, we want to introduce is using the equilibrium about the z directions equal to 0. So basically we have this formula. This is the small force and multiply with the arm distance. So basically that is the shear component about this point, for example. So we have such a formulation. So in magnitude, we come up with this important information. So in magnitude, the two shear stress components has the same value. So which means we come to our diagram here. These are the shear stress in x plane pointing to y direction, which is different from this shear stress because that is simply the two different entities. However, their magnitude, here again, I want to emphasize their magnitudes are equal. Such relations will be very useful in our later calculations, and we're going to use this kind of the important relations again and again throughout this class, mechanics of material. And again, this relation saying in magnitude, okay, in magnitude they are equal. So on the other side, so okay, they are in magnitude equal doesn't mean the two entities are equal, because the entities about the stress not only on which plane it lies on, but in which direction it's pointing to. So they are different quantities. Again, here is in magnitude. Okay, for here I want to emphasize here. So we can look at here. So in magnitude, we can identify which two are identical. Tau yz equal to tau zy. So where is zy? The two quantities are equal in magnitude. And tau zx in magnitude equal to tau zx. Okay. And then final one, tau xy equal to tau yx. Okay, those are in magnitude, they are equal. Okay, that's it.